This question is from the Unit 2 paper from June 2018. Here's the question. As you can see, it's a very long question, so as usual, I would advise you to read it through very carefully. Read it through 2 or 3 times, so it would be sensible at this point to pause the video and come back to it after you've read it through. Provided that you've spent enough time reading through it, and provided that you're familiar enough with the content of the syllabus, you should recognise this as a mechanics question, and furthermore you should recognise it as a question on the topic of kinematics. If we just focus on the first sentence here, this tells us something about the detail of the situation. We're talking about a vehicle moving along a straight horizontal road. Straight is a fairly key word there. It indicates that we're going to be considering a one-dimensional kinematic situation, and although it's not pointed out to us explicitly, we're going to model the vehicle as a particle. So it's going to be a one-dimensional particle kinematics problem. If we just look ahead a little way into the question before we embark upon part A, we see that in parts A, B and D, we're being asked to calculate distances and times. Well, that's a reasonably standard thing in kinematics. But it's really important at this stage that you also take a glance at part C to see what part C is asking you to do. So we will, at a later point of the question, have to plot a velocity time graph. It's useful to notice that at this point of the question before you start on it. If it were me, I'm usually quite often tempted to draw the velocity time graph quite early on in the question, but if they're telling me to draw it later on, then I should definitely resist the temptation to draw it at an early stage. There's a reason they put it at part C here. The examiner wants me to do the velocity time graph in part C. That presumably indicates that he or she does not want me to use a velocity time graph to answer either parts A or B of the question. So let's stick with the schedule set out in the question. Let's start with part A. So here's part A. I've already drawn attention to this point. We're being asked to calculate a distance. So where do we start? Well, the part of the question which describes the initial part of the motion is here. It's the third sentence and part of the fourth sentence. Again, it may be that you need to read those top few sentences through a number of times before you've grasped what's going on. The key thing here is that the motion that's being described is motion at constant speed. So this is the simplest type of kinematics, one-dimensional motion at constant speed. This part of the question is actually a GCSE question. I know that I need to use the formula distance equals speed times time. If I just look up at the highlighted part of the second and third sentences at the top there, I've got a speed and I've got a time. And again, here's where you need to be a little bit careful. There's a couple of stings in the tail, a couple of curveballs that the examiners put into this very long question, and here's the first of them. The examiner has given me a quantity of time which is specified in minutes. You need to be on the ball enough to notice that and to convert it to seconds. So the speed is fine, 15 meters per second, that's the appropriate SI unit, but the 2 minutes I have to convert that to seconds before I do my calculation. Okay, 15 times 120, that's 1,800. You'll notice that I didn't put the units into my calculation as I was working through the calculation. I think it's a good idea to do it this way in mechanics, otherwise you'll have a lot of letters floating around, and it's possible you'll confuse the letters that are abbreviations for metric units with letters that stand for physical quantities. Like M could stand for mass in other questions. So my habit is to leave the units out until the very end of the question, or the very final part of each part of the question, And then also I tend to put them in using the full word for the unit, so meters. Not quite always, but meters, just so I don't confuse a lowercase m with mass, although in fact in this question there is no mass. Okay, so during the first 2 minutes of the vehicle's motion, it travels 1,800 meters. We could write this in kilometers, I suppose, but there seems no good reason to do that. So as usual in maths, don't do anything that you're not asked to do or that it will not prove to be useful later on. Step 2. The second component, the second phase of the motion of the vehicle as described here, is here. That's the second part of the fourth sentence of the description at the top. So in this case, we're told that it's not moving at constant speed, but in fact there's a constant deceleration. You need to get your head around that. You need to understand what that means. You need to be aware that constant deceleration means constant negative acceleration. That's by far the most straightforward way of interpreting that. Okay, and now you've got to make a connection with something that you've learned as part of the Unit 2 mechanics specification. I should recognise now that motion with constant acceleration is analysed using the SUVAT formulae. So here's how I would set out SUVAT. I would write the letters SUVAT in a column going downwards, all lowercase SUVAT, and then I'd look through the question. It should be that 3 of these quantities are specified in the question. One of them is the one I'm being asked to calculate, and one of them is irrelevant. I'm not told it and I'm not asked for it. Okay, so in this question, because I've highlighted in part A there distance, it's distance, or rather S, as you probably know, stands for displacement rather than distance. And in fact here is the second sort of curveball that crops up in this question. The examiner very carefully uses the word distance. Does he or she mean displacement? Well, we're not quite sure at the moment, but let's bear that in mind as a possible potential problem later on. Okay, in this phase of the motion, remember that the vehicle had been travelling at 15 meters per second, so the initial velocity before we start the deceleration phase is 15. Again, I would suggest that you don't put the units in here, just put the numerical values. Okay, and then a typical thing to look out for is what's the final velocity. The key phrase here, it comes to rest, so final velocity is 0. Acceleration, okay, well, I'm not told what the acceleration is. That's ever so slightly unusual. It's not unheard of, but there is something that's quirkily a little bit unusual about this question. So I'm not told the acceleration. So I look at the question, am I asked for the acceleration? Well, no. So in fact, it's the acceleration, which is a quantity that won't crop up in the SUVAT formula that I'm going to use. And then finally, the time taken for this deceleration phase, it's there staring me in the face, it's 12 seconds. So I now look at my SUVAT arrangement there, SUVAT. I need the formula that does not involve A. Here's what I suggested was a little bit unusual. This is one of the formulae that does not crop up quite so often. But if you're on the ball, you should learn all 5 of the SUVAT formulae. And the one I need here is this. S equals U plus V over 2 times T. So it's the mean of U and V times T. And again, I wouldn't mess about here. Whatever quantity I'm being asked for, I would just substitute the numerical values that I've got in first, and then do whatever calculation and algebraic rearrangement that's necessary. So S, I don't know, so I'm going to leave that as S. U, I can see on the left, is 15, V is 0, and T is 12. So there I've entered those into the formula, and quite handily in this case the unknown is still on the left hand side, so I can just put that into my calculator and I get 90. Again, if I call to mind what the quantity is, it's a distance or possibly a displacement, so it should be in meters. Okay. This distance displacement issue, again, let's keep it in mind. Is that an issue here? Well, it turns out it's not much of an issue in this part of the question. So step 3, I need to total these two distances or displacements. So remember, in the constant speed phase of the motion, the vehicle travelled 1,800 meters, and then in that deceleration phase, a further 90 meters, total 1,890 meters. And that's it. That's 3 marks worth of calculation, which seems reasonable enough. Let's move on to part B. Okay, we're given an extra couple of sentences of description here, or 1 sentence of description, and then we're asked to calculate something. At this stage, it might be a good idea to draw a little diagram, not a graph, an actual representative diagram of what's going on. The vehicle is travelling initially from A to B. Now, most people imagine things going from left to right, so let's draw A on the left, B on the right. This is a spatial diagram. It's not going to be a graph, it's a simple sketch diagram. The vehicle is travelling, in the initial part of the question that we've just been dealing with, from A to B. So at the end of part A of the question, the vehicle is at B. So at the beginning of part B of the question, the vehicle is at B. We're told that the vehicle then reverses. Okay, and with a constant acceleration and then constant deceleration, and comes to rest at C, which is between A and B. So let's just mark that on there. Okay, the situation is something like that, and I'm now asked in part B of the question to analyse simply that part of the motion from B to C. Okay, and there are 2 phases to this motion. The first phase is this. Now, straight away here, an issue is going to arise. I need to decide, am I going to take what was previously I picked the direction from left to right as the positive direction, as I did in part A of the question, or am I going to analyse this part of the question completely separately and start counting from right to left as the positive direction for displacement and velocity and so on? Okay, the choice is up to you. But what I would suggest is, having looked through part C and part B of the question, in the later parts of the question, we're asked to consider the whole motion together. So if we chop and change, that's not going to help us. I would strongly advise that you stick with the convention that we have adopted so far. So we're going to go for imagining in our diagram that you've just seen, the direction from left to right is still the positive direction. We're definitely told this phase of the motion is constant acceleration, so again, it must be a SUVAT problem. So here's SUVAT. Okay, so thinking it carefully through, in this phase of the motion, I'm certainly not told the displacement, how far the vehicle travels, and also I'm not asked for it, so S is the thing I don't know and don't need. Okay, at B, the start of this phase of the motion, remember the car was stationary, it was at rest, we were told, so U is 0. Am I told V? No, I'm not told V, but a quick glance through the question, a quick look ahead suggests that it's V, the final velocity for this phase of the motion, is what I need to be calculating. That it is in fact -2, reverses with a constant acceleration of positive 2 meters per second, means in fact that the acceleration in our left to right is positive sense is -2. And if you like, it's the word reverses there that has given that negative symbol. And the time taken for this phase of the motion is definitely 8 seconds. So which of the SUVAT formulae does not involve S? Fortunately, it's the easiest one of all, and the one you imagine that almost all students would remember. V equals U plus AT. Again, don't bother to rearrange it, just plug the numbers in again and then see if you need to rearrange it. So V, I don't know, U is 0, A is -2, T is 8. When substituting negative numbers into a formula, always put them in brackets. I'm very well aware that you could probably do this in your head. You could certainly do it on your calculator. The examiner would like to see what you're doing. So get into the habit of writing it down on the page. So unless I'm really careless, I get V equals -16. Is that reasonable? At the end of this phase of the motion, that the car is travelling, the vehicle is travelling with a velocity of negative 16 meters per second? Well, yes, it is. The vehicle is still reversing at this point. It was stationary, and then it reversed, it sped up. That's what constant acceleration means. Okay, and is now travelling backwards, hurtling backwards at 16 meters per second. Now, there's another phase to this motion, so step 5 now. Then, after that point, it undergoes a constant deceleration of 1.6 meters per second squared, coming to rest. Well, that makes sense. It's reversing at 16 meters per second, then it starts to slow down to rest. Okay, this is constant deceleration, so again, I can use SUVAT if I'm careful. Again, in this part of the question, S, the displacement, is not given and not asked for. U, the initial velocity for this part of the motion, is what we have just calculated, negative 16. V, again, magic word there, rest, comes to rest, V is 0. Acceleration, well, deceleration, remember, is reversing with constant deceleration. So if you like, that's a double negative. The reverses and the deceleration means the acceleration is positive 1.6 meters per second squared. And it's time that I'm being asked for. Again, the SUVAT formula, which does not involve displacement, is again V equals U plus AT. Stick the numbers in. This time the unknown is on the right, but this is pretty easy to rearrange. Again, I'm sure you can do this in your head, although I wouldn't risk it. But you should get, there we go, t equals 10 seconds. So putting step 4 and step 5 together. There were two phases of the motion. There was reversing with constant acceleration, then reversing with constant deceleration. And the two times were 8 seconds and then 10 seconds. So that's a total of 18 seconds. Okay, and that should be the answer to part B of the question. And because of this idea of the vehicle being in reverse, part B is perhaps the trickiest part of the question, and it's not really surprising that that's the part of the question that's worth more marks than any other part of the question. Let's go on to part C. So this is the velocity time graph. 3 marks, there's quite a lot of work to do for 3 marks here, I think. So here we go. Start by sketching some axes. Okay, when I say sketch out some axes, all you need is a ruler and your pen or pencil. You need to draw 2 perpendicular straight lines. If you're on the ball, you will notice that I only need positive times, but I need both positive and negative velocities. At this stage, do not put any numbers onto the axes. A sketch graph does not have to be to scale. You don't have to measure out units on either axis. However, you do need to label the 2 axes. In a velocity time graph, the velocity is on the vertical axis. So you should label it with the word velocity and indicate the units to save you having to write the units all the way for each of the numbers you're going to write on the vertical axis. The standard way to do this is velocity divided by the unit, which is meters per second. If you prefer, you can do the slightly more basic way, which is to put the units, meters per second, in brackets. That's okay. Horizontal axis then on the velocity time graph is time, measured in seconds. Okay, let's see what we were told. Again, if we cast our mind back to part A of the question, there was a constant velocity, constant speed, part of the motion, where the speed was positive. I'll put some numbers on the axes in just a moment. Then there was a deceleration to rest. Then when it came to part B of the question, there was reversing with constant acceleration. In the velocity time graph, that would look like this. Now, we didn't actually work out the acceleration on either of those last 2 segments of the graph, but if you do care to look back at the numbers, you will find that the second of the 2 acceleration phases there should be steeper. I'm not really sure that the examiners will be too bothered if you don't notice that. Okay, and then there was the deceleration to rest again in the reverse motion, which would look like that. Okay, so next I've also indicated the maximum velocity. That was the initial velocity, sorry, 15 meters per second. And then the maximum speed when the car was traveling in reverse. That was when I was doing part B. The first part of B, I think it was step 4, I end up with V equals negative 16 meters per second. So that's showing there. I can also put all the timings onto the time axis now. So 0, the initial time, 120 seconds, that's the 2 minutes of the constant velocity phase, then a further 12 seconds of deceleration, then 8 seconds of reversing acceleration, and then 10 seconds of reversing deceleration. Okay, and that's it. That's what's meant by a sketch graph. 2 axes, which is just 2 straight lines with an arrowhead at the appropriate end of each axis, labels on your axes, plus numbers on the axes corresponding to the key points of the graph where there are changes in behavior. Okay, and just for clarity, and this is for your benefit rather than the examiner's benefit, the 3 points in the motion of the vehicle A, B and C would be identified with these positions on the time axis. The vehicle was at point A initially at time 0. It was at point B at time 132 seconds into the motion, and at point C at time 150 seconds into the motion. Okay, we're ready to tackle part D now, which is determining the distance from A to C. Okay, this looks innocuous because it's only 2 marks. However, I think this is a bit of a curveball question because the examiner has said distance. And if I'm honest, I think the question is lacking a little bit of clarity, but we'll come back to that perhaps. So, what you need to show an awareness of here, as far as the examiner is concerned, is this. And this is why this part of the question comes after the velocity time graph. The distance travelled in each phase of the motion is the area between the graph and the time axis. So the examiner wants us to use our graph to calculate the answer to part D of the question. He or she hasn't said that and won't say that, and it's for you to know that. So let me put the graph back up again. Okay, here's the graph with all its detail. Okay, let's break the motion down into its various components. Okay, the distance from A to B, I need to work out this area. That's the distance travelled during the constant speed part of the motion. So the area, that's just a rectangle, that's 120 times 15. Okay, and then plus this triangular area, well, base is 12, height is 15, so the area is a half times 12 times 15, which is 90. And adding those two things together, I get 1,890. I'm sure some of you would have noticed that I needn't have done that in 2 separate chunks, actually. I could have just worked out the area of a trapezium. That's absolutely fine if you're confident with that, entirely up to you. But I get, for the distance from A to B, so that's distance AB, 1,890 meters. I now have to work out separately the distance from B to C. Okay, and there's something significant here. The fact that the graph is below the axis indicates that as a displacement, the displacement would be negative. However, the examiner hasn't asked for displacement, he or she has just asked for distance. So what I need to do is to work out this area here. So again, if you like, you break it down to 2 right-angled triangles. It's entirely up to you. But it's quite possible to do as a single triangle. So half base times height, half times 18 times 16. Okay, and I get an area. Remember, area can't be negative. Area of 144. Okay, so according to my calculations, A to B is 1,890 and B to C is 144. So the distance from A to C, and if you could call to mind the little diagram I drew before, with A on the left, B on the right, and C somewhere in between, then the distance must be given by this calculation. The distance from A to C will be 1,890 minus 144, which is 1,746. And again, have the patience to write the correct units in your answer. Many of you who are familiar with how these things go and are familiar with the mark schemes, you probably have noticed the examiners don't often take marks off for students leaving out units or for getting units wrong. But I mean, that's no excuse for being cavalier about it. Okay, so that's a 4-part question, plenty of marks, plenty of work to do, and quite a lot to get right. Let's now review some of the skills that we needed to bring to the table in order to answer this question. Okay, long question, lots of skills, all fairly basic. A lot of students would find this type of question, if I could put the length of the question to one side, one of the easier topics in mechanics. The SUVAT formulae and velocity time graphs quite probably is one of the easier sides of the mechanics component of Unit 2. But it's not to be sniffed at. Okay, firstly, the problem was all about, as I said at the beginning, kinematics. The examiner is testing your understanding of kinematics. Specifically, he or she is testing that you know how to model the kinematics of particle motion in one dimension. In this case, it's rectilinear motion, motion in a straight line. Kinematics is the study of motion. Yes, what mathematical tools do you need to analyze motion? And that's motion without reference to what's causing the motion. So you may remember right at the top of the question in part A, the very easy, it's always nice to have an easy part of the question straight off the bat, right at the start. There was a constant velocity phase of the motion, so we were able to use the GCSE speed, distance, time formulae. We used distance equals speed times time, I think, didn't we? Okay, so that's nice and easy, and that was a nice, easy, just 1 or 2 marks to get us into the question, I think 1 mark. Okay, but then a couple of other bits of the question were more substantial and were more specifically A-level and involved constant acceleration. Whenever we see that phrase, something like constant acceleration or constant deceleration, we should know that the examiner is expecting us to use the SUVAT formulae. Please remember that there are 5 SUVAT quantities, SUVAT. Make sure you understand what all of them stand for. Make sure you learn all 5 of the formulae. There was one little tiny bit, but again, it was hidden right early on in the question. It could have messed us up if we got this wrong. A time was specified earlier on in the question as 2 minutes. We need to know that that's 120 seconds. Of course, you know that, but the examiner has quite deliberately slipped that into the question to see if you're on the ball, if you're being careful. Mathematics is very much a question of right and wrong, and this idea of just taking care over things is hugely important. Okay, so don't make silly mistakes. In other questions, of course, they will sometimes ask for a final distance in kilometers rather than meters. So again, just be on the ball. Don't throw away the odd mark here and there unnecessarily. One more thing, really important here. In the SUVAT formulae, but also in the speed, distance, time formula, you need to take care with directions. Velocity, displacement, and acceleration are vector quantities. They have a specific direction associated with them. In one-dimensional rectilinear motion, the direction is indicated simply by a sign. Okay, I would urge you to go back over part B of this question and make absolutely sure that you understand my choices of sign. I did hint at the time, there is an alternative way of modelling it. You could have reversed direction when you started part B of the question and take B to C as the positive direction. I would still suggest to you that's not a wise choice. And then the other big component of the question was the velocity time graph in part C. And that was a pretty standard thing. I have to say, in many of the past papers from the old specification, many of the velocity time graph questions are, I would suggest, a little bit simpler than the one we've seen there. The one we've had is quite a toughie. And again, they weren't desperately generous with the marks. So the examiner is clearly expecting us to be well up on our practice with velocity time graphs. It's worth taking a few minutes to consider the wider skills and connections with other parts of the syllabus that are hinted at in this question. Well, we saw that the question was all about kinematics of particle motion in one dimension. And in particular, the various phases of the motion were either constant velocity or constant acceleration. So, one way in which the question could be made more difficult is, what if we were posed a question in which the acceleration was not constant? Now, you need to be very much aware of this because this is on the Unit 2 syllabus, whereas it didn't used to be on the AS level mechanics syllabus. So you need to be aware that when dealing with non-constant acceleration, you've got to throw the SUVAT formulae away. You can't use them. You can't use the distance time velocity formulae either. You've got to use calculus. That's the only way of analysing problems in which the acceleration is not constant. Another way in which the problem could be linked to something much more complex is, what about two-dimensional, three-dimensional motion of a particle? Well, if you haven't seen a little bit of that already, you will be seeing that later on. And the key thing there is, in order to describe the motion in 2 or 3 dimensions of a particle, you're going to have to learn to use vectors. Rather trickier, what if you try and extend our model from a particle to something else? Well, something else could be a number of different things. The next obvious thing from the point of view of A-level mechanics is what we would call extended bodies. So rather than a particle where all the mass is concentrated at a point, what if the mass is extended? For example, a rod or a beam, or more complicated again, a lamina, or more complicated again, a three-dimensional solid body. Fortunately, we do not have to worry about things like that at the moment, but just to put things into context, that's where this kind of study would go later on. And some of the things I've mentioned just there aren't on the A-level syllabus at all. It's a bit too advanced for A-level. One final thing that's definitely is on the syllabus is you need to have a good understanding of kinematics before you embark on a study of dynamics. Dynamics is the study of moving bodies in which you try to make a link between the causes of the motion and what the motion is. Okay, so in kinematics, we're just told essentially how the body is moving. We're told about the acceleration and asked to infer things about displacement, velocity, maybe time, and things like that. In Newtonian mechanics, the heart of the study is that you understand what forces are acting on your particle or other body, and from that you make a link using Newton's second law of motion to acceleration, and then from the acceleration you use kinematics to tell you something about the motion of the body. Again, that's studied quite extensively in the later units of mechanics. Well, a little bit in Unit 2, a lot more in Unit 4, and then much more again in the further maths modules.